It's time for a new chapter. Chapter 4 is all about exponential functions and their inverses, which are called logarithmic functions. In section 4.1, we're going to introduce exponential functions. Let's do it with an example. Suppose a population of rabbits starts at 600 and grows by 60 rabbits per year. All right, that's a pretty simple situation that's familiar to us. That's just linear growth. We've got a rate of change here that's a constant. If p of t is the population after t years, let's write a function for p of t, the population after t years. I know that my slope is 60 because that's my rate of change, 60 rabbits per year, and that my initial value is 600. Pretty straightforward. Could have asked this problem way back in the first couple weeks of class. Suppose instead that the population of rabbits still starts at 600 but grows by 10% each year. This is a different kind of growth. If you think about it, it's not linear. It's not going to grow by the same amount each year. It's going to grow by a constant percent rather than a constant value. This type of growth is known as exponential growth. I'm going to look at t and p of t in this context. All right, we start at time 0 with 600 rabbits. After 1 year, well, the initial 600 increases by 10% of 600. Does that make sense? So that's 600 plus 60, or 660 rabbits. Another way we could calculate this, so I'm multiplying 600 by 10% and then adding back my original 600. Well, I could really do 600 times 1 plus 0.10. Does that make sense? So that it's really 600 times 110%, so that we get the original 600 and the 10% growth. So this would be another way to calculate it. This will be helpful because we're going to try to find a pattern here. After the second year, we're going to take that 660 from the previous year and multiply that by 110%. So you can see it's going to grow by a little bit more than just 60 rabbits this year. 660 times 1.1 is 726 rabbits. After the third year, well, I'm going to take that 726 and multiply that by 1.1. 798.6. I'd probably round that up because obviously we aren't going to have 6/10 of a rabbit. After the fourth year, I'm going to take that value times 1.1 again. You're kind of seeing the pattern here, hopefully. If we keep doing this, really for any year t, we should be able to multiply the previous one by yet another factor of 1.1. So if you think about it, it's our original 600 multiplied here by, well, 1.10 times, then multiplied by 1.1 once. Then that value, which already had a factor of 1.1, multiplied by another one, and another one, and another one. So if we think about an exponent, I want to multiply by 1.1 t times. If we can go back here and think of this as, 600 times 1.1 to the 0. This is 600 times 1.1 to the 1. This would really be 600 times 1.1 and that value times 1.1 again, times 1.1 again, times 1.1 again. So we get this kind of expression where our exponent is our variable. That's where the term exponential growth comes from. And we get a function p of t that looks like this. Our initial amount of rabbits times 110% to the power of t. I want to just show you this graphically. So we looked at both linear growth of the rabbits, which is of course this red graph, and then exponential growth, which we can see starts to grow a little bit faster. If we zoom out a little bit, we can even see that difference is a little bit more extreme. So you may have heard that phrase exponential growth to mean something that's growing really, really fast. And yeah, growing by this percent is a lot faster than just growing by 60 rabbits each year. I'd I'd like you to watch this video with another example of exponential growth.
How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1,000th of a centimeter in thickness. That is 10 to the power of minus 3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of the newspaper. Now, we begin to fold it in half. How many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2,000ths of a centimeter in thickness. If we fold it in half once again, the paper would become 4,000ths of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again, always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1,024 thousandths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper, we can go very far, but very fast too. Summarizing, if you fold a paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then, starting with a piece of Bible paper and folding it 45 times, we get to the Moon. And if we double it one more time, we get back to Earth.
All right, so pretty extreme example of how these exponential functions grow really, really fast. Let's just try to model this situation for a minute. If x is the number of folds and f of x is the thickness of the paper, well, it's said without folding it at all, it's 0.001 millimeters. Then when we fold it once, it doubles to 0.002. That comes from taking 0.001 times 2, doubling it. We talked about growing by a percent. Well, this is really multiplying by 200%. We want the original amount and an additional 100%. After our second fold, well, we're going to multiply 0.001 times another factor of 2 to get 0.004 millimeters of thickness, etc. Eventually, if we just let x be the number of folds, well, 0.001 times 200%, and we're going to do that x times. We could model the growth in the video example with the function f of x equals 0.001 times 2 to the x, doubling every time. get to an official definition of an exponential function then. The exponential function with base a is defined for all real numbers x. I want to talk about that a little bit more to be, in case you're suspicious of that. But it's defined by f of x equals a to the x, where a is greater than 0 and a is not equal to 1. So, a few more details about this. In general, the domain is all real numbers. Of course, it might be restricted by the physical situation, like in the previous example, the number of times we fold it had to be positive integers. But in general, we could plug any real number in for x in this function. So you might be thinking like, oh, what happens when I have a negative value of x? Well, we can calculate something like 5 to the negative 2. That's 1 over 5 squared, or 1 over 25, if you remember your exponent rules. And if we think of an approximation for pi, we can even approximate 5 to the pi, which is an irrational number. Sure, we can figure out about what it is, 156.99 if you plug that into a calculator. So we can take any real number for that exponent x, giving us a domain of all real numbers. There's an assumption here that a is greater than 0. Why is that true? Well, we would have a problem if we had something negative for our base a. Think of f of x equals negative 2 to the x. Well, it starts going back and forth between positive and negative values, right? If I had negative 2 squared, that's positive 4, but negative 2 cubed is negative 8. And so it just makes for kind of a messy function, bobbing back and forth between positives and negatives. So we're going to stick with a positive base value. We're also going to assume that it's not 1, mostly because that function 1 to the x is just 1. So it's a constant function. That's no fun. It's kind of boring, so we're not going to include that with our exponential functions. The functions that we've seen so far, they don't fit our exponential function definition above exactly. They're actually transformations of the function above. If you think of our rabbit example, it's 600 times an exponential function. So all that does is vertically stretch it by a factor of 600. And similarly with our thin piece of paper being folded, it's just a vertical shrink of the exponential function with base 2. So our previous couple examples are a little bit different, but they're just transformations of our exponential function. Notice that for both of those examples, and in general it'll be true that this will be our starting value or our initial value. Let's talk a little bit about what the graph of an exponential function looks like. We already looked at the graph for our rabbit example a little bit, just to compare it with the linear function and see that rapid growth. Let's take a look at the graphs of a couple of other exponential functions. Let's take the function with base 3, 3 to the x, and then we'll compare it also with the function with base 1/3, just to see how those compare. Again, our base is always positive. So I'm just going to cut to the chase here. If we plug in some values and make a table of values, a couple comments on this. I would maybe pause and make sure that you agree with all these calculations, remembering exponent rules like 3 to the negative 3 is 1 over 3 cubed. Remembering rules like 3 to the 0, anything to the 0 power except 0 is 1. So some of our exponent rules are hiding in here. If you take a look at the two graphs, well, y equals 3 to the x exhibits that rapidly growing motion that we just talked about with the first couple examples. The function with base 1/3 actually goes downhill rapidly. So sometimes exponential functions grow, sometimes they decay or go downhill. The difference is that value of the base. Turns out if the base is greater than 1, it goes uphill. If it's between 0 and 1, it goes downhill. Here's an observation that might help us justify that. Notice that if we take our function 1/3 to the x, it's really, well, 1 over 3 to the x. If we distribute that x, it's 1 to the x over 3 to the x. And if we play with that a little bit, that's the same as 3 to the negative x, right? It would be 1 over 3 to the x. And 3 to the negative x, we would expect to be a reflection of 3 to the x about the y-axis, right? F of negative x. So In our previous example, we could have obtained the graph of g from the graph of f with just a reflection about the y-axis. Here are those graphs again. We can see 3 of x reflected about the y-axis is 1 over 3 to the x, and vice versa. So in that way, I might think of expecting functions with a base bigger than 1 to go uphill like this and less than 1 to go downhill. Here's just a graph of a bunch of exponential functions with different bases, just to see some general patterns. So to the left of the y-axis, the ones that are headed downhill, we can see our fractions between 0 and 1 for base. And those that are going uphill have bases that are bigger than 1. And as we might expect, as that base gets larger, we have a steeper, more quickly growing graph. You probably are also drawn to the fact that they all pass through the same point, 0, 1, and that makes sense. Let's just summarize some observations with all these graphs. So for one thing, all these graphs pass through 0, 1 because anything to the 0 power is 1. So for every base, whenever we plug in 0, we get 1. If the base is between 0 and 1, it decreases rapidly. And if the base is bigger than 1, we've got an increasing function. So exponential decay versus exponential growth. Another observation, the x-axis is a horizontal asymptote for this function. So we've got a horizontal asymptote of y equals 0. If we look at this graph again, if I were to draw a horizontal line in here along the x-axis, yeah, that line y equals 0 is definitely a horizontal asymptote. The graph approaches it on the left if it's an increasing graph, and on the right if it's a decreasing graph. Finally, we mentioned that the function has a domain of all real numbers. Its range is all positive numbers. I'm not going to be able to take any base to a power and get a negative output. So for our basic a to the x function, all of our output values are positive. I'm also not going to get 0 as an output, so from 0 to infinity for our range. Here's just a summary of that. This is a box from your book. It's got all that information we just talked about. Here's the graph of an exponential function. Let's see if we can figure out what the equation is. So we'll need to determine what that base is. Just like we expect, it passes through the point 0, 1. It also passes through negative 1, 1/5. That's really the only other point I can read for certain on this graph. If we think of f of x equals a to the x and the point negative 1, 1/5, what I know is that an output of 1/5 corresponds to an input of negative 1. This should help me find the base value of a. A to the negative 1 is 1 over a. If I multiply both sides by a and then multiply by 5 to undo this, it looks like a is 5. Or you could probably see this even earlier on. 1/5 is certainly the reciprocal of 5. This means that this is a base 5 exponential function. Here's one for you to try. Find the equation of this exponential function. Just an observation. This should have a base that is between 0 and 1 because this graph is decreasing. It is exponential decay. Try that and post in the homework discussion for homework 7. Let's talk about an application of these functions. Our first one's going to be about compound interest. Suppose you invest $1,000 in a bank account. The bank generously gives you 5% interest, compounded annually. Compounded annually, let's sort that out a little bit. When interest is compounded annually, that means the first year you earn 5% on your initial $1,000. That initial $1,000 is called your principal. In the following years, you earn interest on the $1,000 and interest on your previously earned interest. Let's look at what that means. I'd like to write a function for the amount in dollars in the account at the end of t years. Let's maybe start thinking about this by making a table of values. I know that we start with $1,000. After 1 year, well, I've got $1,000 and I've got an additional 5% interest. So as we discussed before, if I multiply by 1.05, that's 105%, giving me my original $1,000 and an additional 5%, $1,050 after that first year. My second year, what makes this interest compounded, earning interest on your previously earned interest. This time I'm going to take the $1,050 and 5% of that is going to be my interest for the next year. So hopefully you can see that means our interest is going to be a little bit more than $50 that second year. I can calculate it by taking, well, here's what I have at the end of the first year. I'm going to multiply that by another factor of 1.05. If I do that, at the end of 2 years, I've got $1,102.50. So you can see here we earned $52.50 interest that second year. Interest on our interest, that's the idea of compounding. If we repeat this after T years, I think you can see we're going to have our initial $1,000 and we're going to multiply it by 105% T times 1,000 times 1.05 to the T. So here's our function. A of T is 1,000, which was our principal, times 1.05. That's 1 plus our percent. 5% is a decimal, so we have 105% to the power of T. All right, here's our function. Let's use it to determine the amount of money in the account after 20 years. Well, that should just be A of 20, which is 1,000 times 1.05 to the power 20. We'd be multiplying by that 105% 20 times. So 1,000 times 1.05 to the 20th is about, I'm going to round it. It makes sense since this is money to round it to 2 decimal places for cents. This is $2,653.30. How much would be in the account after 4 years if the principal amount was $2,000? Well, let's see. In this case, if my principal is $2,000, my equation looks like this. And that's about $2,431.01. All right. Do these on your calculator along with me. Make sure you see how to type this in correctly. By order of operations, we don't want to do this multiplication before we do the power. One more question on this. How much would we have in the account after 10 years if we invested $2,000 at 0.75% interest? Oops, that's supposed to say interest, sorry. Compounded yearly. So let's see, in this case, my function is going to look like 2,000 times 1, well, 0.75% as a decimal is 0.0075, so 1.0075 to the T. And after 10 years, I want to calculate this, 2,000, 1.0075 to the 10th. This is about $2,155.17. Most banks give interest more than just annually, more than once a year. Suppose our bank decides to calculate interest quarterly or 4 times a year. In that case, if we have a 5% annual interest rate compounded quarterly, our quarterly interest rate, well, I'm just going to take that 5% and divide it into 4. So each quarter we get 1.25% interest. What makes this different, though, is each quarter we get interest on our interest. So ultimately we end up with a little bit more than that 5% at the end of the year. If we invest $1,000 at this rate, apologize for these typos. If we invest $1,000 at this rate, how much is in the account after the first quarter? Well, I'm going to take that initial $1,000 and at the end of the first quarter, I'll have, well, 100% plus 1.25% as a decimal would be 0.0125%, and this is just once after 1 quarter. That's going to give me $1,012.50. After the second quarter, well, I'm just going to have to do this again. Multiply by another factor of 1.0125. That's going to give me $1,025.16. At the end of the first year, well, 1 year is 4 quarters, right? So I'm going to be looking at this expression. Oh, I should be approximating here, by the way. I think we're doing some rounding. After 4 quarters, $1,050.95. Again, I'm rounding to the nearest cent with money. Okay, how about this, the 20th year? Well, 20 years is really 80 quarters, right? So I need to take 1,000 times 1.0125 to the power 80. This is about $2,701.48. This time, let's suppose we invest $1,000 at a 5% annual interest rate compounded every month. So our monthly interest rate, in order to calculate that, we'd want to take our 0.05 and divide it by 12. Let's keep it in that form rather than trying to approximate it. I don't want to approximate too much before we get our final answer. In general, try not to round until the very last step if you can. Let's look at how much is in the account after a month. So I'm starting with $1,000. I want 100% plus this 5% divided into 12 months. And I want this just once for the amount after 1 month. This comes out to $1,004.17. After 6 months, well, same expression to the 6th power. This is about $1,025.26. A year, this would be 12 compounding periods. So the same expression to the power 12 is 1,051.16. Go ahead and pause and make sure that you're getting the same thing typing this into your calculator. It's kind of chunky to type in to make sure these parentheses are in the right place. The exponent is incorrectly. So give yourself a chance to try these in your calculator and let me know if you're not getting what I'm getting. Finally, after 20 years, well, let's see, 20 years is going to be, well, 20 times 12 compounding periods. And once I do that calculation, I get $2,712.64. Exponential growth is fast, but I'm multiplying by something that's just barely bigger than 1, so it's not going to give me an obscene amount of money, but after 20 years, my money's almost tripled, so it is growing pretty quickly. Let's see if we can generalize this. A general formula for A, the amount in the account, in terms of P, our principal amount, T, time in years, R, the annual interest rate is the decimal, and N, the number of compounding periods per year. So putting together what we've been doing, we're going to take our principal times, well, 100%, and then our interest rate divided into the number of compounding periods. So here's where we had 0.05 over 12. And up here, I need to take T, but T is time in years. In order to get the right number of compounding periods, I'll need to multiply by N. In order to get the correct number of times to compound this, I need to multiply by N. Just like back here, we had to multiply by 20 times 12. 20 years times 12 compounding periods. Here's our general formula for compound interest. Trying this one more time, say you invest $5,000 at 2.8% annual interest compounded quarterly. Well, 1 plus 0.028 as a decimal over 4 compounding periods. How much is in the account after 10 years? Well, that's 40 compounding periods. This is about $6,609.20. Let's think about this. One more question. Suppose you want to have $5,000 in 10 years. How much must you invest now in an account paying 3.8% annual interest compounded quarterly to meet your goal? This is going to be called present value. What's the present value of our money? So I actually want my answer to come out to $5,000. I don't know what I want to currently invest, so I'm going to let principal be a variable P. This is 1 plus 0.038 over 4 for quarterly compounding. And in 10 years, that's 40 compounding periods. P is going to be 5,000 divided by all this stuff. And this is approximately $3,425.45. That means this is what I need to invest today if in 10 years I want to have $5,000. Here's just a general statement generalizing what we just figured out about compound interest.